Good afternoon. I think that someone is got it. Yes. Okay, so I say, good afternoon, and thank you very much for being here for this first in-person colloquium after a long time. And it's a pleasure, and I'm delighted to introduce you, Professor Daniele Struppa. Let me briefly introduce Professor Struppa. Dr. Struppa earned his laureate in mathematics from the University of Milan in Italy in 1977, and he received his doctorate from the University of Maryland, College Park in 1981, and held the position at the University of Milan, and then in Pisa, Scuola Normale di Pisa, and University of Calabria, where I met him 30 years ago. So then he moved to George Mason University, where in 1997 he was selected as Dean of George Mason College of Art and Sciences, and since 2006, Dr. Struppa has been Provost and then President of Chapman University in California, where he founded the Institute of Quantum Studies. Then Dr. Struppa continued because he's first and foremost is a scientist and continued his scholarly research focusing on Fourier analysis and its application to a variety of problems, including signal processing and pattern recognition, applied also to biomedical issues, including proteomics of cancer cells. He's the author of more than 250 refereed publications. He published several books and chapters. And in recognition of his work, he had several awards. There is a long list here, but it's worth to mention the Cozzarelli Prize from the National Academy of Science. And on behalf of the department, Daniele, thank you very much for finding the time to be here to talk about your research, and the floor is yours.
Thank you. Well, good afternoon, everybody. Thank you, Pino, for this very nice, exceedingly nice introduction. I'm very happy to be here. I'm happy to be the first face-to-face speaker in a long time. It's been a long pandemic for all of us, so it's kind of nice to be able to get together again. I'm a mathematician, so I hope I'm not going to disappoint the physicists. The way I would describe my talk is a physics-inspired talk, but it's more math than anything else. But I hope you find it of some interest, because the phenomenon that is underlying all of this is a physical phenomenon. I also found it intriguing that this is my pointer, in a place where you have so many fancy lasers. No, they did offer me a laser, I have to say, but I thought this would be really kind of cooler. Also because it's useful when people get distracted, you can quickly reach out to them. I have an anecdote, but it's, time is short, so I'll get on with the topic. So there are three ingredients to this talk today. One is the Talbot carpet, one the Gauss sums, and one is superoscillations. Talbot carpet is a optical phenomenon. The Gauss sums are a number theoretical object, and superoscillations are a lot of things. I know them mostly because of their mathematical significance, but they're really a phenomenon that we see in optics, even though their origin are from quantum physics. And what I like to do is to give a sense of each one of these topics and then show how they kind of come together. And their coming together is actually should not be a surprise. And as I point out here, is a joint work with three colleagues of mine. Colombo and Sabadini are at the Polytechnic in Milano, and Alain Higet is a professor at the University of Bordeaux in France. Where I was talking with one of you before, that's where I gave my very first professional talk, maybe 30 years ago. So this is the scheme of what I'm going to do. I'm going to do a very brief excursus on the Talbot carpet, the Gauss sums, what are the superoscillations, and then we're going to see how they connect and give us the real topic of the result. The real original results, there is a collection, like most colloquia you find. There's some stuff that was known, some other stuff that is known but you interpret differently, and then some stuff which is new. The new stuff is going to come at the end. It's a little technical, but I hope you'll appreciate what the meaning of it for it. So this is a book from 1650. 1665. And it's the first time that the term diffraction is used by an Italian physicist, Grimaldi. And in one of these chapters, it mentioned what is called a proposition 1. And the proposition 1 says, light propagates or diffuses not only directly or by refraction or by reflection, but also in another fourth mode, diffraction, which he puts in capital letters there. So the first time that this word is used, apparently, and of course the Talbot carpet is a very good example of this phenomenon. So the situation is the following: you have a screen here, and there are regularly spaced periodic openings, and the lights come through here, and then the light produces these images, these beautiful images that are a result of diffraction and how the ray of lights combine. And there are several things that one notices here, and I summarize them in the next slide, but I mentioned them here. You notice that so there is a distance at which you replicate exactly the same image. That distance is called the Talbot distance. But if you go halfway, you see that you have another image of this of your original conditions, but it's shifted. The period is shifted halfway. So as you notice, this image corresponds to the middle. And then if you go to a quarter, you see that now you have again the original grid, but now with half period. And then you go to 1/8, and you get again half in the period and the shift. So it's a beautiful image, and again, it's just a result of diffraction, and this was published in 1836. And here I have just the summary of what I just said. The actual formula for the place where you're going to have the same image as you begin is lambda over 1 minus root of 1 minus lambda squared over a squared. But if you use the binomial expansion for the square root, this is approximately 2a squared over lambda. So when lambda over a is small. So that's all I'm going to say about the Talbot carpet for now, and we're going to come back to it later. So the only thing I need, those of you who haven't seen it before, I believe many of you probably already saw it in your classes, but if you haven't seen it before, the only thing I want you to remember is that there is a grid with periodic openings, and the image of the grid is replicated at a certain distance, and then halfway you kind of have the same with some shift, and you keep repeating that image. That's all that will be necessary for what follows. Shifting completely topic, I want to go in very brief excursus on number theory. I was telling Professor Strangi, this paper has been kind of influenced by the fact that I'm teaching a class on number theory, so you get interested in trying to look at different things. So there is something in number theory is called the quadratic Gauss sums, which are, you see here the explicit expression. Now, these are what, if you forget about for a second the L square, what you see to the pi I A over C, these are roots of the unit. So what you have is a sum of suitable roots of a unit. Okay, and in certain conditions, these are going to be actually primitive roots of the unit, which means that period produces all of them. This particular expression was used by Gauss, was introduced by Gauss, we believe the first time, in Disquisitiones Arithmeticae, which is one of his masterpieces, with which he proved the so-called Quadratic Reciprocity Law. Now, Quadratic Reciprocity Law is one of the most important results in, what you say, early number theory. Gauss used to say that this was one of the theorems he was the most proud of. I think the most proud was the construction of the regular polygon with 70 sides, but this was something he called one of the most elegant theorems. You know, given what Gauss has done, if this was considered a great theorem by him, I think we can take that to the bank. I'll say in a second what this quadratic reciprocity law says, but essentially the problem that Gauss was looking at was to solve the equation x squared equal p. Now, x squared equal p, you can't solve it, obviously, but if you do modulus q, for q another prime number, then sometimes you can, sometimes you can't. So the quadratic, what is this called the quadratic residue problem. So you want to solve the equation x squared equal p modulus q, where p and q are prime number. And the question was, is the relation between this question and the question when you switch p and q, and you do x squared equal q modulus p. And so that's what the quadratic reciprocity law says. And Gauss, by the time he came up with the theorem, he gave, I think, something like 6 different proofs. Yes, sir. I'm sorry? Oh, bigger? You know, I can try, but I'm not sure I'll be successful, but let me try. Is that a little bit better? Let me, yeah, you're right, that exponents there is kind of nasty. So now I'm going to be bigger, but then I'm going to have trouble later, but I'll figure out the trouble later. So, but let me read it for you. So the exponent is 2 pi I, and then a L squared over C. L is the number I go between 0 and C minus 1, and A is the parameter. So the root of the unit that you have are e to the 2 pi I A over C. And what I do, I add them up, multiplying by this L squared. Now I can see the entire image, but it's okay, we can manage that. So to tell you, so these are very computable. It is possible to compute it. There is a famous theorem, which in fact is a theorem by Gauss, the so-called Gauss Formula, that says that, yeah, it says what is written here. I'm not going to read it. But it's the solution to this expressed in terms of this symbol, which is called the Legendre-Jacobi symbol. So it's not a quotient. It's not A over C, but there is a kind of thick parenthesis, A over C. And this symbol is 1 if the problem that I mentioned before is solvable. In other words, you have a solution x squared equal p modulus q is minus 1 if problem is not solvable. In the quadratic reciprocity law says that if you take p over q over b in this sense, so you take the Legendre, the Jacobi symbol for p and q, and you multiply by the Jacobi symbol for q and p, then you get minus 1 to p minus 1 half times q minus 1 half. So it's a very powerful theorem. Forget about the specific technical number that come out, but it's very powerful because it allows you to calculate once from the other, and it really allows you to calculate the symbols, which are very important for a wide variety of number theoretical questions. One of the examples I always give my students in class is if tonight you go and you pick up some money at the ATM and you use your ATM card and you punch in your code, that code is transmitted after an encryption that is really based on these ideas. The fascinating thing is that the RSA method that we use to transmit very delicate information is fundamentally based on a theorem that came out from Euler and Gauss. So sometimes we say, I don't know how useful some part of mathematics is. Well, this is a lesson that it's always too early to say that. So these are the Gauss sums, but there is a generalization of those Gauss sums that also play a role. And this, I'm going to read for you what the exponent says for everybody. So these are now, you have 3 numbers. So you have the sum of e to the 2 pi I, and then now the exponent is a little fraction. The denominator is c, the denominator is a L squared plus bl. So it's the same as we had before, except that there is an extra bl. So there is a linear term. So again, is sum for L from 0 to c minus 1 to e to the 2 pi I AL squared plus BL over C. And so clearly the old Gauss sums are just a particular case when B is equal to 0. Now I think the rest of the notes are not so small, so I'm going to go back to the previous magnitude that should allow me to project the entire picture every time. Okay, so those are the 2 ingredients. The first ingredient we said, Talbot, with diffraction when you have this periodic grid. The second ingredient, Gauss sums, kind of an interesting object related to the units of unity, the roots of unity. The third ingredient are superoscillations. So what are superoscillations? This is how they were defined, I think, in one of the first papers would appear, maybe the first paper will appear. So they're functions which band limited and yet can oscillate faster than their highest frequency, at least on a small area, which is called the area of the domain or interval of superoscillation. I mentioned before, they originally came from a work of Yakir Aaron, who is a colleague of ours at Chapman University, and Albert and Weidman, in which they introduce a notion which is called weak value. We don't need to work on weak values today, but so it's a different kind of way of extracting information from quantum system. And in working on that particular notion, they encountered this phenomenon. But maybe the person that made this known throughout the physics community, not just the quantum physicists, was Michael Berry, Sir Michael Berry, Bristol. And maybe this is the paper that most contributed to the popularization of this idea, called Faster Than Fourier. And Sir Berry has done quite a tremendous amount of work in this direction. And from an optical point of view, you can actually see them, and I'm going to show you what the mathematics behind it, but you see them when you have a ray of light being diffracted by nano holes. So if you have a structure with very, very small holes, then you can recreate this effect. So let me see what these superoscillations are. It's a very widely appearing phenomenon, but there is what I call the prototypical example, because every paper you will ever read on superoscillation begins with this particular case. So this is a very innocuous looking function, because I'm sorry, I don't know why. Oh. Let me take this away. Okay. So it's a very innocuous looking function, right? It's a cosine of x over n plus IA sine of x over n, all of this power n. So there are two remarks that can be done on this function. The first one is that you can replace the cosine and the sine with the expression that you have using the Euler formula. So the cosine of theta is what? Is e to the I theta plus e to the minus I theta over 2. The sine is e to the I theta minus e to the minus I theta over 2i. So you can do that substitution here. You get e to the I x over n, e to the minus I x over n. You factor them out, you play a little bit with them, and then you apply the power of the binomial. And when you do that, what you get is this new expression. So here you see that we apply the power of the binomial because you have this n over j. So essentially you have these are all the frequencies that appear now are 1 minus 2j over n, j going from 0 to n. And the coefficients Cj's are oscillating coefficient. See, there is a minus 1 to the j. Minus 1 to the j comes from the fact that you have a plus 1 and 1 minus a. The 1 minus a obviously is negative because a is bigger than 1. So I take it out. So now it comes here. And here you have this quantity that is going to go like a to the n. So these are very large, highly oscillating coefficients. So that's the first thing you can do with that sum I just wrote. Just calculate it, replace, and that's what you get. But there is another thing that you can do. Let me go back for a second, and then I'll skip to the next slide. You can say, well, but let's take the limit. What's happened when n is large? Well, when n is large, the cosine behaves like 1 minus x squared over n squared. And the sine behaves just like x over n. So when n is large, the x squared over n squared is irrelevant. So what I'm left with is 1 plus IA x over n to the n, and that's the exponential. And I take n going to infinity. So the second property that appears is not only I can rewrite the function in this way, but I actually notice that this is the limit. Its limit is e to the IA. And that's why they're called super oscillating, because we have that Fn has all the frequencies at n are bounded by 1. You remember j goes from 0, in which case this is 1, to n, in which case this is minus 1. And yet the function converges to e to the IAX, uniformly or compact sets, for a arbitrarily large. That's where the name of superoscillation comes into the picture, because it appears that I can generate very high frequencies, even starting with bounded frequencies. Now, the key to this, of course, it looks like, how can that happen? But the key is when you look at this formula, is the fact that the Cj depend on n. So this is not a series that I'm truncating at n, and then I take n larger, and it's converging. Every time you increase n, you're actually recalculating the coefficients. So that's the reason why this is possible and is not mathematically as surprising as it could be. So there are lots of questions that one can ask about the superoscillations, and there are now several groups in the world working on this. Professor Strange was asking me before, there is a very strong group in Bristol, of course, most related to issues of optics. There is a very strong group in the University of Toronto, Rochester, and Tulane. And so there are different kinds of questions, some of which are very applied, how you create them, how do you make them happen on a concrete situation. And that's, I know, is something that Professor Strange and his team are more interested in. And then there are mathematical questions. The first was, can you get other examples? I mean, this is this example everybody uses, but is this a more frequent phenomenon? Is there anything special in those particular frequencies that we are using? Another very interesting question, for which we don't really have yet an answer, so this is a good question for people who are math-oriented, is the following. Think about analytic functions. What is the big deal about analytic function? The big deal about analytic function is that if you know everything in the origin, and when I mean everything means value and all of their derivatives, then I know the function everywhere. That's kind of a big deal. That's why analytic functions are so important. That's why it's so different from simply infinity function. Here we have a sort of a similar phenomenon. Let me go back for a moment, because here what I know the value, the exponential in this case, but as we showed, but not really, but as I can tell you, this applies to a very large class of function. I know the function in a lot of points near the origin, right? To me to calculate this sum, I need to know 2 endpoints, and then as n goes upward, it becomes infinitely many points, and these are all points of this form 1 minus 2j over n. So now I know the function in a lot of points near the origin, and that allows me to calculate it everywhere. So there is some sort of similarity. So the question that we ask, and the answer is no, but we're trying to figure out what is the right question then. Is this an equivalent way of describing an analytic function? Could it be that you define analyticity by saying a function is analytic when it has infinitely many derivatives and it's expressed by those derivatives? F of x is the sum of 1 over n factorial fn at 0 times x to the n. That's one definition. The other is the function has this property that you can write f of x in a point x by just using what happened near the origin. The answer is no, but it's very close. So we are trying to figure out exactly in which sense it is. One of the questions, though, that we've been working on, and that was one of the first questions that Ronald asked, is about the evolution of this. So if I take the Schrödinger problem and I start with a superoscillating function, will it evolve in something that is superoscillating? And this is going to do two things. The answer to this is, for a large class of potentials V, the answer is going to be yes. But the other thing that is useful is, as we do this, we are going to produce actually a huge amount of new superoscillating situations. And that could be of interest in a different set of sections. So I'm not going to prove this, but I just want to very quickly describe the general strategy for addressing the problem. Well, you start with your Cauchy problem. You take a superoscillating function, or, as initial value. Then you compute the solution. And how you compute the solution? Well, in some cases, so I'll show you one example. You can do it just by inspection, very simple, when v is equal to 0. In many other cases, you're going to have to use the Green's function. And then you try to show that this new object that you found actually is superoscillating. In other words, this object only uses the value of a function in a small interval to produce values far away from the origin. The way we do this, and I'll show it in a second, is through some kind of fancy topological considerations about the topology of the spaces in which these objects are. And I'll go very surfacey on that. But I should say that I actually, last week I had some visitors at Chapman from Washington University, St. Louis, and they have a different method to do this same approach that actually use the momenta of the green function associated to the potential V. So that's kind of interesting because that approach, when you look at it at the very end, it is almost isomorphic to our approach because also involves at the end a continuity argument to be able to switch some limits, as I'll show in a second. But it really looks a very different kind of coefficient. So I think there will be an interesting to see how that can be incorporated or connected. This came out, I gave a talk at Washington University, then some people in the audience got interested and decided to work on that, and I think they've done some really nice progress. Okay, so this is the simplest case. Suppose you just take V equals 0 and you see what happens. Then the solution, so you start with our superoscillating, so that's, remember, it's cosine of x over n plus IA sine x over n power n, or better to think as a sum of exponentials, e to the I kj x, where the kj is 1 minus 2j over n. Well, then it's obvious, oh, that's what I use here, the kj. It is obvious that this is a solution. Why? Well, you simply take the derivative, and you take the derivative with respect to x twice, you get this coefficient coming out. And then you take the derivative with respect to t, and you get this coefficient coming out. And because of the sign here and the sign there, then things actually work out. So you can just, it's a 1 minute calculation that this is in fact the solution to the problem. And, oh, sorry, I went to the wrong direction. Okay. The next step, so what I just showed you is the first step in every one of these superoscillating problems, which is find the solution to the Cauchy problem. The second step is to show that this solution actually can be seen as some series of infinite derivatives on the function fn. I think the calculation in the next slide, but this shows that the solution to the Cauchy problem can be obtained from the initial condition by applying this kind of operator. And those are the kind of operators that we're going to be interested in studying. Now, in general, the operator is going to be much more complicated because the operator will depend on V, on the potential. In this particular case, the potential is 0, so the operator is actually fairly benign looking. Why is it true that psi can be written in the way? Well, oops. You can skip the calculation, but the thing is that you write the exponent as an infinite sum, you aggregate the terms, and then this comes out. I mean, we really don't need to waste time in verifying the calculations. I promise you they're right. And so what we have is this operator, and this is a strange operator. I call it, during the course of the talk, I usually call it an infinite order differential operator because there are infinitely many derivatives. People in analysis correct me because this is a little bit of a more delicate nomenclature, but so I'll just skip of that. But I have that my psi n is this operator, we call it u, applied to fn. Now, I want to know what is the limit of the psi n. Remember, that's what you want to do, right? You have the psi n, which is what is exponential calculating those point kj's. And the key point, and today at lunch, I was telling some of you, some of your colleagues here, that the first time we wrote this paper and we sent it to, I think it was Physics A, or the Proceeding of the Royal Society. I don't remember which one of the two journals, but the referee complained about the big deal that we made in going from here to here in exchanging the limit and the operator. He said, well, you know, why do you have to waste all this time? But that is the key part of the proof. So here, this operator is an infinite series of derivatives. So there is no reason a priori why you can bring the limit inside. And to prove that that's the case, I guess that's a math job, the mathematician's job. So when the referee said, well, you know, we don't need to show that, we said, no, we really need to show that. So I think we eventually prevailed, and the publication has the proof. But this is the delicate point of the argument. So the operator U, you show, is acting continuously on the space where these functions are. And because of that, you can switch it, but now the limit of the Fn is just the exponential. And so you have the operator apply to exponential. And so you prove that you now have a new super oscillating sequence. Because we don't have too much time, this I tell what the infinitary differential operator is. And I think this is important because, as I said, I refer to U as an infinitary differential operator, but this condition is not always satisfied in our cases. And that adds an interesting, for mathematicians, complexity. So let me say what really is an infinitary differential operator. First of all, the definition applies to complex analytic functions. So you have to transfer the problem into the complex realm, which is possible because the example we just saw, and every time we work on those, you have these exponentials, which are really not only real analytic function, but actually they admit entire extensions. So an infinitary differential operator is an infinite series of derivatives such that it acts like a local operator on the sheaf of holomorphic function, which means it doesn't move the support. When you don't satisfy this condition, you have something more complicated, which is what we would call a convolution operator. For example, if I were to take all the derivatives divided by n factorial, simply, so suppose that this is 1 over n factorial derivative, and I apply to the function f of z, what I get is f of z plus 1. So it acts continuously, but what it does is shifting it. So it's really a convolution with the delta in the point -1. So again, when I use the word infinitary differential operator, I use it in a loose sense, and actually the theory that we have to develop keeps in consideration that in many cases the operators you have to deal with are not, technically speaking, infinitary differential operator. That's something a little more complicated. And so this is what we really need to do, which is to prove that these operators are continuous. So in general, these are going to be convolution operators. And fortunately, there is a very well-developed, very advanced theory of convolution operators. My dissertation back, I hate to say, but back in 1981, so it's a long time ago, was on convolution operators on space of analytic functions, so that became helpful here. And so the kind of function that we work here are functions that satisfy those conditions, and so we can actually prove the continuity. Okay. So I think we have completed the kind of the 3 major ingredients, the superoscillations, the Gauss sum, and Talbot. Now, what I just described is not just about function, but you can actually have a similar phenomenon, which we call supershift, for distributions. So, like in this case, you can have that supershift means that now you have a family here of distributions. Is a distribution that depends on a parameter. And so in the case of the exponential, the parameter is the frequency. That doesn't have to be necessarily the case. So it's a much larger phenomenon than one could, spend time talking about this. But let's see what happened for the example that it's crucial to this presentation, which is the Dirac Comp. So the Dirac Comp is obviously always the object that is used to model the Talbot phenomenon, because it's composed of what? Of deltas which are spaced. In this case, the period is 2 pi over m. So 0, and then you have a delta, then 0, and you have another delta, 0, and then you have another delta, and they're equally spaced. We know that because of the Poisson formula, this can also be rewritten in this way. It's an equivalent way of writing, because it's the same as writing the Fourier transform of those. And so the question is, can we evolve this Dirac Comp? The evolution of Dirac Comp is what's going to give us the Talbot picture. So the Talbot picture really is the evolution of the Dirac Comp. And the result, and you won't be surprised because you have seen what I showed before for the case of the exponential, this is the evolution of the Dirac Comp. So if you evolve just one exponential, you saw it before, that's what you would get e to the minus a squared t times e to the IAX. That will be the evolution of e to the IAX. When we evolve the Dirac Comp, we have the series of this. By the way, notice that that's why I mentioned distribution before, because now we are not working with functions, infinity function or analytic function. Now we are working in a distribution sense. So I made a logical jump, but a necessary one. And so here is where the Gauss sums appear in this unpleasant to look at formula, but I have a worse one later. So if you look at this, every value of t, I hope you remember the picture we had at the beginning. Picture we have at the beginning, for t equals 0, you have the Dirac Comp, the grid. As t moves, at every level of t, you have the image in the plane of what happens to the diffraction process. Well, when you go to t's, there are multiples of 2p over m squared, rational multiples. This is what you get. So forget about this. This is just technical because this is really a distribution in two variables. So you still have to keep count of the variable t, but that's just the delta of t in this point. So this means simply that it's 0 everywhere else. So the only point you're looking is just like the restriction. Okay. So what you're really interested in what comes here. So what do we have here? What this is telling you is that when you block t, you're going to have a sum of what? Forget about this coefficient for a moment. This is the delta of x minus 2k pi over n. That was the original Dirac Comp. Minus 2 pi j over n. So you get the original comp with some shift and some variation of the intensity that comes there. Well, but you don't get all of these objects because every one of these objects is multiplied by the Gaussian sum. Now you can say to me here, fairly enough, where is the Gaussian sum coming from? Well, it comes from factoring appropriately this thing. So it's a one page of factor this, take one case and the other, and I can promise you that it's correct. It's just a series of computations that are kind of freshman kind of like of computation. So what happened, and you see, by the way, when you look at the way you're here, you have this exponent and you remember what the Gaussian sum are exactly those things with those exponents. You have a square and you have a linear term. So this is not surprising that it happened. So what this theorem tells you is that at every level of your picture, the image is going to be a sum of the original with some coefficient in front. And now I'm going to give you one very simple example that justifies what we have seen in the picture itself. And that's the example here. So let's take that you take t to be 1/2 of 2 pi over m squared. So you remember I said we're going to look at the rational multiples of this number. So 1/2 means now I'm half in the picture that we looked at. So 1/2, let me go back so you know what happens here. So because P is 1 and Q is 2. So this sum goes from J from 0 to 1, right? Because 1/2 is this P over Q. So if I take that as a particular fraction, I have J that goes from 0 to 1. So I'm going to have only two pieces. So let me see what those two pieces are. So those two pieces are the following. The first one is when J is 0. And the second one is when J is 1. And when J is 0, I have exactly the old Dirac Comp. And when J is 1, I have the Dirac Comp shifted. But now I know from Gauss, our old friend Gauss, that when J is 0, G of -1, 0, 2 is actually 0. So this first part disappears, and I have that my image is going to be G -1, 1, 2 times the Dirac Comp. But that's exactly what you have. If you remember, that's exactly what you get. You get the shift of the same image that you had at the beginning. So this is kind of a fun thing for number theorists in a way, because what we have shown is what we see is that in fact, the Dirac Comp is a theorem in number theory. You can use that. I'm not saying that it's an easy way to use it, but you can use that to optically calculate these very funky sums. When you look at the picture, that's what is written there. To me, it's one of the things I like, and I think you captured this because I said something similar before, is when people do math for one reason, and then all of a sudden, 100 years later or 200 years later, it turns out that what they did really made a lot of sense in a completely different area, right? I guess the first example you ever saw that were the theory of conics that these Greeks did for just because they were curious about it, I guess. They were interested, they were kind of fun to look at. And then when Kepler was looking for the right shape for the movement of the planets, they kind of became really helpful. So that's a long time to wait for your theorem to be powerful. Here, Gauss didn't have to wait that much. So now, what are superoscillations got to do with this? Well, I could calculate using those formulas, but in fact, what I can do, I can remember that every exponential can be approximated by using exponential of finite frequencies. Remember, in this Dirac Comp, I have exponential up to infinity, right? You have all the integers there. And so what I, in principle, and that's the spirit of what follows, though it's not technically what is happening, but what's happening is that you could replace every one of them with a sum of exponential in a limited band. And so what I can do is I can actually have an asymptotic expression for the Gaussian sum. Instead of having the precise expression that comes from there, but that would require that it's kind of really unwieldy and cannot be calculated, I can now make an asymptotic expression. And that's really a very interesting and neat thing. So I have just a couple of minutes. So you take the regularized Dirac Comp. So now I take a function psi, which is compactly supported, and I replace it with the convolution with psi. And so now I'm going to want to evolve this new object. And it turns out that the evolution is what you would expect, which is the convolution of the original Dirac Comp convolution with psi. And now I'm going to put the formula that is helpful to remember. So the one I have here is what we showed before. That when I take the evolution of the Dirac Comp and I stop at a particular value of t, I get this expression, which you remember it means the sum of shifted Dirac Comps times the Gaussian sums. And in particular, this allows me to calculate the action of phi on a compactly supported function. Phi m is distribution. That's why I inserted a short slide on distribution. So it acts on the infinity function. How do I show how it acts? Well, I put it here. I do this acting on psi. Well, this acting on psi is going to be equal to the sum of this times the delta up to a. But because of the support of psi between -1 and 1 and the way delta is fixed, it turns out I'm going to have one element. And so the action of phi over psi is going to be equal to g times 2 pi over n cubed times 1. The 1 comes from the fact that psi, the origin is actually. And so by multiplying by 2 pi over my q, I get this function. So I can calculate precisely the value of the Dirac form by looking at the action of this evolution on a function of compact supporting response. Now, this again is not an asymptotic. This is a precise calculation, but has the inconvenience that the psi m is infinitely many sums. And so what I do here, I will skip this. Okay, so this is the fundamental last result that I wanted to show you. Forget about all this. I have to put the right terms there because if people see the slide, they're going to say, "Oh, it's not true." But the point of this is the following: that you can find some constants which depends on P and Q in particular, some exponential. This omega, I show you to you in a second what this exponential are, but these are exponential in finite band. And the value, by the way, this should be a J, not a K, but okay. The value of my Gauss sum here can be seen as a limit of these finite sums, where I take the value of psi hat in those points. So This is what we call an asymptotic for the Gauss sum. So now I'll show you just for the sake of it, what those C and those omegas are. So you see the omegas are just exponentials. And if you look at the argument of those exponentials, they're all finitely band. And then you can see the C is, you already know where that's coming from. It's coming exactly from that expansion that we saw at the very beginning of the talk. So it's not surprising. It's messy to write down. It's messy to calculate. It's impossible to write in tech without crying, but technically there isn't that much there. So, but the key of the result is that I know exactly what G is, but I don't really like that because it requires an infinite series. And here, on the other hand, I have an asymptotic. The convergence can also be measured. And so we know the speed of this convergence. And so I can calculate as accurately as I want by simply using the value of an arbitrary function, psi, with compact support. And I want to show you just a couple of references. The one on top contains, at least until a few years ago, most of the mathematical understanding of superoscillation is a memoir of the AMS. So it's really very comprehensive. It tells a little bit about how weak values led to superoscillation, but the bulk is about this stuff. It doesn't talk about the result I described today, but it talks about how we can reinterpret Dirichlet series using superoscillations. And that's in the same spirit, frankly, of what the work I just described. This is a very helpful roadmap on superoscillation, the Journal of Optics, led by Michael Berry. It's a collection, if you're familiar with the roadmap series, it's a collection of articles. Every article is very short, it's 2 pages, and it's supposed to be kind of state of the art. So there is a section of mathematics that we wrote, but then there is a lot of stuff that for physicists like you is probably way more interesting. It gives you applications, how they show up in certain phenomena. This is actually, the third paper is a beautiful paper of Michael Berry, which is the first time that the Talbot effect was connected with a phenomenon of superoscillatory nature. It's, you know, when you look at the result, it's very distinct from what we have, but that was one of the inspirations for the work. And finally, this is the paper that contains all the mathematics that I described today. And I think I more or less stick within my time, so thank you very much.
Thank you, Daniele. It was fantastic. I enjoyed a lot.
Thank you.
So now the colloquium is open for questions. Yes, please.
Well, I was wondering about this connection with the Gaussian sum. Is this only when it's a free particle or
Yeah, you need to use that particular expression. Absolutely. Well, we have results actually for, okay, so in our paper, in this paper here, we also deal with the case of general V. But then we don't have the Gaussian sums there. So we can study in detail the phenomenon, and but you don't have any more connection with this number theory object, which is kind of really a curious thing in a way. And the situation of general V is much more complicated, but fascinating in itself. I'm sorry? Yeah. Oh, absolutely, yes.
It seems like a very intriguing connection because even if you can't actually, if you just show the equivalent, you can't calculate the, you know, if you just show the quantum quantum mechanics, you can calculate the object.
Mm-hmm. Yeah, I think it's really kind of a surprising thing. Certainly Gauss never imagined something like that. It's kind of the, I don't know, the beauty and the simplicity of nature in a way. The fact that something like so sophisticated like a diffraction pattern would be embedded in this very simple numbers that are connected to the solution of the quadratic residue problem. It's fascinating. Yes. I'm sorry, how long did it take us? So the connection with the Gaussian sum was first made by Michael Berry, and I don't know how long it took him. He's a very quick guy. So, well, I think that Well, I don't know exactly the answer. One of the things is that when you look at those sums remind you, when you look at superoscillating functions for just one exponential, what you have on top looks like an ingredient of the generalized Gaussian sums. When you take the comp and you have an infinite series, then this looks even more like that. So I think that the connection is not completely unnatural. So when you write it down, then you see, so can I factor them out? And so you know what they look like. And so that's how we went about the factorization. But it's, you know, some of this stuff takes quite a while. I have to share, you know, today we were talking about mathematicians versus physicists. You know, I remember the first time that Professor Aronov came to my home to talk about superoscillations. We had dinner and then we went in the backyard, smoked cigars and went on. So we were playing scotch and talking about stuff. And he gave me this presentation on superoscillation, and I didn't understand virtually anything because it was in such a different language. And it took me, I would say, 4 years or 5 before we actually figured out what he really wanted to say and do. So now when I look back, I say, well, it's obvious, but you know, it wasn't at the time. It took us a long time. The only thing I can tell you is that the very first time he told me stuff, and I said, you know, I'm not really sure, I don't know, I don't understand, but I knew that infinite differential operator was going to play a role because of some of these infinite series of exponentials, and I had some experience with those objects. But why and how I didn't know. But then I think I learned a lot. I learned how to understand different language, and I still don't know very much, but at least I understand some of the language. And I think he enjoyed learning some of this. But with him, I was saying this over lunch, it's always surprising that we have to go to such extremes to prove things that he believes are obvious. Like the fact that the superoscillation phenomenon remains is totally obvious to me. But in reality, I really don't think we can show that it's not an obvious phenomenon. We show that it's also not necessarily true for every potential. So we have cases in which that doesn't happen. So there is something really delicate there.
So if you have a superoscillating function and you want perspective function, what do you want? Because having a one-time visualized noise
right. So when you stop at a certain level, what you have is you have in a region, which goes superoscillating region, you have very fast oscillations, which we have a general big peak in the center and then some smaller one on the side, and then the function goes up exponentially. That's part of it. So you have everything's fine here, and then you have larger and larger oscillations that in fact grow, if you remember the expression, like 8 to the n. So you want to avoid that, so you have to take a larger interval, which means larger n. So now you have a good phenomenon here, but still outside. So it's a phenomenon that constantly escapes you, so to speak. When you fix, so there is a uniform convergence of the compact set. It's not too outside. So that's probably that's a very good point. One of the open questions, for example, that here I don't know thinks the answer is yes, but we don't have a proof yet, so that's going to be like the other case. Is that every time you have a superoscillation phenomenon, so not just the example that I showed today, but every time you have that, then outside the interval of superoscillation, the function will grow exponentially. So that's another, I mentioned an open problem before, I don't remember which one it was, the analyticity. This is another problem which we've been working and we really, it makes sense, right? It's true in all the examples we have, but we've not been able to nail it down. So again, the problem is, suppose you have Fn that is superoscillating converging to some f of x. This means that Fn is a finite sum up to n of exponential with the, limited frequency. And then you can get a function of arbitrarily large frequency. Is it true that wherever that's not happening, in other words, outside of the compact set, the thing explodes with exponential power? So it's an interesting question. And I think I haven't found yet an example where Aaron gave us a thought that it turned out to be okay. So if I were a betting man, I would bet that it's right. But in math, we don't make bets. We try to prove stuff. So And the other interesting problem is the one on analytics. Yeah, these two ideas essentially the same. The answer is they are not exactly the same, but they are essentially the same. And we are, I think, on that very good shape, and maybe next time that I come here, we have to do for that.
I mean, if somebody else has something, I don't have to. But I guess I just want to quickly sort of keep that thing when you're referring to it. It's obvious. I guess I was going to present this point of view and see how you would respond.
Sure.
So that exponential operator written down as a differential operator, I guess we also write down explicitly as an integral operator. And so maybe because you can do that, maybe you're actually maybe I'll argue that then it's okay to work with the integral form, but it's convenient. Is that a
No. I mean, that would be an alternative way of trying to solve the problem.
Yeah.
Definitely. I would say it's probably equally difficult, or not difficult, but equally delicate. I think that the impatience, if I can use that word, the referee was very cordial, but he was saying, I think you guys take a lot of time to show something that it's kind of obvious. Is because I think the referee was intuitively understanding how this was happening, because obviously the referees know that you can always interchange the limit and operator. So you're taking two limits and switches. So I think that probably from a physical point of view, because that's another example in which I think everybody that I talked to kind of felt that this permanence was going to last. But, in reality, it doesn't last too long because you don't take n going to infinity. So if you only evolve a finite Fn, not the limit of Fn. So Fn approximates the exponential value. When you evolve it, it only lasts for a small amount of time, and we can actually calculate exactly for how long. So the fact that it will remain forever, that wasn't solved. And I think that that's where the confusion was, because they saw that this happens. Why would you? But the question is here, we are not looking at Fn representing the exponential, but the sum, which is an infinite sum. But your approach is very valid and it might work. I mean, these colleagues from Washington U have used a different approach, but it's interesting because for us, the ultimate part of the demonstration is the following. You look at the operator, you look at the coefficients, you look at the space in which you are. To act continuously, there are some pretty delicate theorems of complex analysis that tell you the condition of the coefficients. So now you go and using the Green function, you calculate those coefficients and you know that that's true in this particular case. What my colleagues from from Washington U have done, they forget about the coefficient, they don't care about this, but they look at the momenta. And then they have some conditions on those momenta, some growth condition on those momenta that allows them to claim the continuity. So even though it's a different approach, I think ultimately you go back to the same issue. And that's why I thought it was fascinating. I gave a talk maybe a year and a half ago, and this was the math department, so the talk was much more mathematical, and I gave all the details of the proof, and I think that stimulated them to see whether they could avoid it. So yeah, I think there are possibly other ways, but ultimately they will all boil down to that particular stick issue, and there is no way around.
In the program here of the evolution, what I actually mind is assuming this table for the function, the green function method, I should actually be able to guess what are the properties.
The probability potential that we ensure.
In the more general way, because I can use the universe behavior with the green function and use that, and using the answer of the green function to have what I should be able to get.
Well, that would be very interesting. I mean, if we had something like that, would be very interesting. But yeah, I mean, I like to have a theorem that tells me when the green function does this. In fact,
I know the green function which we take universal doesn't matter, but the potential means the wave function. The final answer. Once you assume the behavior, I can guess what is the potential with that.
Okay, maybe we can.
We call this in inverse coding. But using green function, we should be able to do that.
Yeah, then maybe we can take a couple of minutes. Yeah, thanks.
Yes, last question.
So the pattern.
Yes, yeah.
interface of abstracting waves.
Okay, if there are no other questions. I would like to thank you very much, Daniela, for this very nice talk. And I would like to remember that we have a light refreshment outside, so please stay. And thank you again, Daniela.
Thank you.